Let me try something. Can you say something?
No. So, shall we start?
Yes. You can start. Was there some issue, some technical problem?
No problems.
No. Okay.
So let us start. Okay. So on behalf of all the organizers of webinar on PDEs and related areas, a very welcome to all the participants and to Professor Gyula Chato. It is my great pleasure to introduce today's speaker, Professor Gyula Chato from University of Barcelona. Professor Chato obtained his doctoral degree from École Polytechnique Fédérale de Lausanne, EPFL, under Professor Bernard Lecoronier. His research interest lies broadly in the areas of partial differential equations. He has done several important contributions on topics such as Moser-Tudinger inequality, isoperimetric type inequalities, pullback equations, and several others. Let me point out a nice book he has written on the pullback equations. The book contains some chapter on Holder spaces and decomposition of vector fields, which could be of interest to a much broader audience. And today, he'll be speaking on fractional Michael-Simon Sobolev inequalities. Gyula, it's over to you now.
Thank you for the invitation. And I will put the thanks to the end of the talk. For I will. Should I now start sharing the screen?
Yeah.
Okay, I will start. Wait, I have to go here. Share screen. Right, now I have to go view full screen mode.
Yeah.
So it's working properly?
Yes, yes, but...
Oh, wait, I have to go back. What's happened? Okay, sorry. Okay, so I will talk about fractional Michael-Simon Sobolev inequalities. And I start with a quite elementary introduction. So the first part should be understandable for a broader audience. Wait, I have here. I want to see at least some video. Can I see at the same time? No, this doesn't work. Okay, never mind. So this is based on a joint work with Xavier Cabre and Matteo Cozzi. So let me start a very vague motivation, a general motivation, which is on the evolution of shapes. So here I will talk about the special evolution where you have a domain which changes with time. So these are different times and goes more and more towards the form of a ball. The goal is to decrease the surface area with time. So these are some physical examples that you can imagine. A drop of oil in water, right? In the beginning it has a shape and then it quickly becomes a ball, or population of species 1 and population of species 2, and they have some contact on the boundary, which let's say is not a good contact. They quarrel, they fight, and they don't like each other. So they will want to minimize the boundary where they have contact with each other. And so the aim is to decrease surface area with time. Another example would be a soap bubble and the air. So the blue is the inner part, for example, soap bubble and the air. And here also the soap bubble quickly becomes the form, changes its form to become a ball because it minimizes surface area. So the mathematical model for this kind of behavior is evolution by mean curvature flow. This is here in these examples, it's volume preserving because while the way I drew the picture, it's volume preserving because the volume stays the same of one of the species, for instance. So let me explain the mathematical more precisely. What is the equation of mean curvature flow? So here I have a set omega t, which depends on a parameter t. So we have a family of sets. Here I have drawn the blue one is the omega at some time t. Well, the boundary is the blue one, and the red one is the boundary of omega t at some later time, t plus delta t some. And here, oh wait, I have to go like this. Perhaps, okay, oh, this works better. Okay, so x will be some point on the boundary, and h is the mean curvature. So here h, here in just a plane, of course, you only have one curvature. So the mean curvature is the curvature. So here you have high curvature, here you have curvature 0, and here you have, let's say, negative curvature, right? And the equation is that the time derivative of the point x of t, which is on the boundary, is minus the normal. Mu is the outer normal. So here the normal points outwards. So because of the minus sign, here you go inwards, right? Is you multiply by the mean curvature. So at this part where h is 0, it doesn't move. And here where h is negative, because of the minus sign, the boundary moves outward. Oh, so this is very sensible, this mouse. So it sounds touch a little bit too much and it jumps 2 steps ahead. Sorry. So this is mean curvature flow. And if it's volume preserving, then you have to subtract the average of the mean curvature. I will not talk about the volume preserving case. So here, let's say if you have a ball, then of course this is constant, and it's constants minus the constant. So for a ball, nothing happens if you have volume preserving mean curvature flow. So I have drawn here some pictures. Okay, the pictures are not, okay, I drew them myself, but they're not completely original. It's, I took the same pictures as I saw in a very nice talk by Golding or Minicozzi, I don't remember. They're very nice talks on YouTube on the mean curvature flow. So my emphasis is not the mean curvature flow, but I will start motivating the results. So here, if you have a ball, it will shrink to a smaller ball. This is mean curvature flow, not volume preserving. If you have a cylinder, then it will shrink. Right here you have the normal goes outwards like this. It will shrink to a line. If you have a form like this, okay, we are in 3 dimensions here, domains in 3 dimensions. Here you have very high mean curvature. So this will shrink quickly to a line, this middle part. Let's say perhaps somewhere here you have negative mean curvature. So it will, in the beginning, it will go a bit outward. And here you have also positive mean curvature. So it will go a bit inward, but not as fast as here. So then it will get disconnected, and with time it will be more and more like 2 small balls. You can see as I move the mouse, right? Where I'm pointing at. Is the question, Prosenjit?
Yes, you can see it.
You can see, okay. I just want to be sure because it's the first talk that I give like this. The classes I give differently on the board, on little board. So, and of course, the simplest case, if the mean curvature is 0, let's say your domain is the half space, your initial domain is the half space, its boundary is just the flat, and so the mean curvature is 0, so nothing happens with time. So let me recall an important property. If you have initial domains omega 0, 1 and 2, right, and one is contained in the other, then they will be contained in each other for all times. Actually, the distance between them will stay strictly positive. If they don't touch, they will never touch the 2 boundaries. Okay? So this is the monotonicity. And so if you have a bounded initial domain, then you can put it always in a big ball of a radius, which is at least the diameter, right? And so you can calculate very simply the evolution by mean curvature of a ball. It's the evolution of the radius, essentially, right? So at t equal to 0, you just have r0, additional radius, initial radius, and as t gets bigger, this gets smaller until it gets 0, right? It gets 0 exactly at this time, right? If t is this value, then this is 0. And so with this, you get an extinction time for any bounded domain, right? Because any bounded domain is contained in some big ball. So because of the monotonicity, after this time, right, the ball vanishes and the other domain has to be inside. So you see here you have R0 square, so you have something of the order of the diameter of the domain square. Right, this is a very rough estimate. Because imagine, okay, let's, these are in 3 dimensions. 2 pictures in 3 dimensions. Imagine a domain which is like a cylinder, and it's very, very long, but very thin. Of course, here the diameter, let's assume, is much, much bigger than this radius. But here, okay, this will shrink very fast. I mean, you can make it as small as you wish, this radius of this of the section of the cylinder, with keeping the diameter the same. So this estimate is quite bad for this domain, if the radius is much smaller, because the diameter can be very big. Or an even worse example, here I take a domain with diameter, infinite diameter, right? But bounded perimeter. Right? For such a domain, this is completely useless. So it would be much better to have an estimate of the extinction time in terms of the perimeter. Okay, so this was precisely obtained when a famous paper by Evans and Spruck. Okay, they have many other results, but among them is the extinction time in terms. Okay, I'm just this message from the Zoom covers part of this. Is this happen only to me? The Stoppstelle is right above the exponent of the boundary of omega. Is this only for me like that, or for everyone?
We can see it perfectly.
You can see perfectly. Only I cannot see perfectly. Okay, then I don't care. Okay, so you can see the exponent, the perimeter of omega 0 to some power.
2 by n, right?
Yeah. Okay, if you can see it, then it's fine for me. I just cover some message from Zoom, which I cannot. Okay, then it's fine. So let me talk about the crucial ingredient of the proof of this result for the extinction time. It's a universal Sobolev inequality on submanifolds of Euclidean space. So this was obtained by Michael-Simon and Allard. And let me explain it in 2 steps. So first, I just write the classical Sobolev inequality, right? The LP star nu bound by the gradient, the LP norm of the gradient. So like this is the well-known one, okay? But here I put the gradient of the manifold, right? The tangential derivative, tangential gradient. And if you do this on a manifold like this, it doesn't hold true. Okay, you have to add an additional term. I will give immediately an example why this has to be like that. Okay, the manifold is in Rn plus 1, but it is n-dimensional, right? N-dimensional. So that's why this is, if you imagine Rn in Rn plus 1, you just get the classical Sobolev embedding. Okay, what you have to add is a LP norm of U. And you have to multiply it. Well, you don't have to. If you want here a constant, which is independent of the manifold, then you can get it precisely if you multiply here by the mean curvature. Okay, H is the mean curvature of your manifold. Okay, if you don't care about having this constant independent of the manifold, it's not so difficult to obtain such an estimate, and you can just put here U to the power P. But then you get a constant depending on the manifold. Just by using local parametrizations, you can get an estimate like that, and doing the thing in the flat and using the result in the flat case. Okay, so why this has to be like that? Okay, of course, Sobolev inequality is equivalent to isoperimetric. So this is also true on a manifold. So imagine that you have, let's take an example of the sphere and a subset of the S of the sphere. E is a subset of the sphere. And you plug in here, well, you plug in P equal to 1 and U the characteristic function. And then you get here the perimeter within the manifold. And here you get the measure of the set E to some power, right? So you get, this is the power. Well, I'm on a 2-dimensional manifold. You get the measure of E is smaller than its perimeter, right? But this cannot be true alone, right? You can take E very big, set very small perimeter. So you see, you have to add something. And the thing that compensate will be exactly the mean curvature. So how does this Evans-Brook result use this result? He uses exactly in this setting where actually he takes E to be the whole set, the whole boundary of the set, which evolves by mean curvature, right? And then you get here, this part is not there. It's like taking U equal to 1, and then this thing vanishes. And you get here the integral of the mean curvature. And the point is that this constant does not depend on t, right? That's how he uses this universal Sobolev inequality on manifolds. Well, okay, so now I repeated first the classical setting, and now I will talk about non-local things. So for non-local things, I will introduce first the non-local perimeter. Okay, here also some message covers my screen, but okay, I think I remember what is there. So here I have a set E, and I define the non-local perimeter of E as a double integral. It's integral over the set E and integral over the E complement. Okay, the x's are in the blue and the y in the complement. 1 over this very singular kernel x minus y. So you should, if you compare with my first slide, my initial motivation for mean curvature flow, I was saying that let's imagine two populations which avoid each other and want to have as little contact as possible. Let's say they fight, they quarrel on the boundary, but you can imagine something like now they also shout and curse each other and call each other names, and that you also hear a bit from further away. It's philosophically, it's something like that. You have to take into account also interactions further away. But if you go far away, you don't hear that much, this shouting and the cursing. So it's not that bad, not that annoying. But if you're very close, then it disturbs more and more, right? Imagine that the two populations avoid each other like that, that they also notice the people further away. Okay, so this is, okay, why I take this kernel. Okay, this kernel you can also imagine other kernels which have been studied broadly, but this kernel, like this to this power, distance to the power, this is the canonical kernel. It's like the minus Laplacian is like the canonical elliptic operator in that sense. So what does this have to do with the classical perimeter? Why do we call this a perimeter? So there is this limiting property if s goes to 1. Oh, now I see what is covered. The parameter. Here it's 0, s smaller 1. I cannot see it because there a little message appears talking Gyula Chato. Okay. So that is the, so if s goes to 1, this becomes very singular. This is not integrable anymore. So, and here in front you have a constant, which will go then to 0. I will explain this in the next slides. So anyway, this perimeter, if the parameter s goes to 1, will go to the classical perimeter. Okay, but before doing that, okay, I will do a little heuristic calculation. I will give just a very simple example. So if you have, I compare two domains, E1 and E2. E1 is the union of two balls with distance d1 from each other, and E2 is also union of the same two balls, but with a bigger distance, right? So in this case, the classical perimeter will be, which is the boundary of the two balls, right? In both cases are equal. But you can simply check simple estimates that the perimeter, the fractional or non-local perimeter, in the first case is smaller than in the second case, right? You can imagine again the two populations, the blue ones which are inside avoid the ones outside, and the blue ones in some sense like to be closer to each other. They're in some sense, they also feel each other in the distance. Okay. Right, so let me do a heuristic argument, what this has to do with the classical perimeter. So here I wrote down again the same thing, and now I wrote explicitly the constant will behave like 1 minus s, this constant in front. As s goes to 1, this goes to 0. So let me look at this double integral. So if you have, let's take a tubular neighborhood of the boundary. The boundary is the black part. I drew a black part, and a tubular neighborhood in both. There's the inner tubular neighborhood and the outer, the blue one and the red one. So I claim that actually if you take the limit of this as s goes to 1, you can forget about the interactions, whatever epsilon is. If you take any epsilon, you only have to take into account the interactions between the two tubular neighborhoods. Okay? So I'm omitting here all the interactions between all the blue ones here inside and all the ones in the complement outside without the tubular neighborhood. And another one too, vice versa, from the outside and inside. So let me show you why you can. It's easy to see. So let's say I omit. Okay, let's say. Okay, this goes. I didn't want this picture yet, but okay, let's omit this one. So E is inside the blue part, right? And the red part, I look at the interactions in the complement of the set E, but without the tubular neighborhood. So outside this red tubular neighborhood. So if now I will do a very, very generous estimate. So if X is in that set E, right, but the Y is outside of the tubular neighborhood in the complement, right, and this tubular neighborhood has distance epsilon, then instead of taking the Y's just there, I take all the Y's outside this ball of radius epsilon, right? So I replace this set by this set. Okay, it's a very generous estimate. And now this is a simple radial integration, right? Because I'm centered around X. So I can calculate this explicitly, right? And here I get some value. And if S goes to 0, right? This goes to 1, I mean, to 1, this goes just to 1 over epsilon. And don't forget there's the factor 1 minus S in front. 1 minus S in front. So this will go to 0. So whatever epsilon is, I can omit in the limit. If I take the limit, I can omit the faraway interactions. So now if you take epsilon very small, okay, this is what I said already, that this limit will be to 0 because this goes to 0. So for very small epsilon, now you assume your boundary is smooth enough, then for very small epsilon, you're like in a flat case. Okay, this actually the previous part was not heuristic, was completely rigorous. The heuristic argument is this, that here I'm not so precise with the estimates, but I say that for small epsilon, like in the flat case, and all you have to show now is that this double integral, the interactions with this part, this blue part below and this red part below, are proportional to this to the length of that you're taking. That's all you have to show in the limit. Huh? Okay, so you have to show that such a double integral, if you let S go to 1, this will be proportional to the area here of the part that you're taking, okay, independently of epsilon. Okay, so this is a simple calculation. Okay, I do not do the details, but you write out, you separate the integrals vertically and horizontally. And actually the horizontal integration is, you call that a constant Cn. And one of the integrations is actually independent of where you are because it's whole Rn minus 1. So you simply see that it's proportional. And in the end, you just get the one-dimensional, two-dimensional integral, okay, from the vertical one. And when you calculate that explicitly, that's when it cancels out with the 1 minus S, okay, because of the power here. When you integrate twice, there will be a 1 over 1 minus S. And that's how you get, okay. I do not do here the details, but I just put this here if someone wants to look at the talk again, and then he can easily fill in the gaps, I think. Okay, this was the most difficult calculation of my talk. So now let me talk about the non-local mean curvature, right? Because I started with the mean curvature. So how do I define the non-local mean curvature? So here I have a set E, right? I have a set E and I do little variations of the set, right? I take a function phi, which is defined on the boundary, right? And I take at the point X, right? I look at the point X plus T times phi times the normal, right? Here I go outwards. Here if phi is negative, I go inwards, right? And like this, I construct, I construct a full family of sets, right? For t equal to 0, I get my original set. For small t, I'm very close to my set. Actually, I will look only at small t. Okay, this is a variation of my set E. Well, I define the variation of the set E by varying its boundary. So now recall that the mean curvature, okay, is the first variation of the perimeter in this sense. If, okay, this new set, this ET, has a perimeter too, right? Has a perimeter, and I can derive the perimeter with respect to t and evaluate at t equal to 0, and I get the integral of the mean curvature times phi. So this is, so I use exactly I define implicitly using this same idea, the mean curvature, the non-local mean curvature, which depends on the parameter S. Well, what do? I do the same variation, and instead of putting here the classical perimeter, I put here the non-local perimeter, the fractional perimeter, right? And I do its variation, and then also that I can write, one easily sees that one can factorize a phi in the integrand, and the other function which appears, which will depend only on the set E, is some function hs. Okay, hs is the first variation of the non-local perimeter. So explicit form, I wrote here down the explicit form is for a point x on the boundary, it's a solid integral, okay? Integral over all y in Rn, calculated. Okay, I have this on the next slide again. Let's go to the next slide. I have this, right, I have it here too. Okay, so this is the explicit form. So you have integral of the characteristic function of E complement minus the characteristic function of E. And you have the principal value. The best thing is to give you an example. Right? I calculate the fractional mean curvature of a convex set. Then you see how you, okay, using this expression. So E is a convex set, and I take a point on the boundary, right? So I have to calculate the integral over the whole space. Okay. Oh, sorry. So here you see. Okay, here's the principal value. So principal value, I mean exactly that. I take the whole space minus a ball centered at x of small epsilon, and I let epsilon goes to 0. Okay, so I calculate this integral because of the principal value. So I do a radial integration, which I center at x. Okay, and for each fixed radius, right, I have to integrate along a circle. Okay. And this is my integrand. So I integrate on the circle of radius r of this expression. Okay. So here, of course, now I'm on the circle, and x is the center. So this will be constant. This will be just 1. This will be r to some power. And here I have, when y is in the complement, y is in the complement of the set, that's the red part that I have as the red part. And here comes the contribution when y is inside. That is the black part, right? So that's here it's a 1 and here it's a -1, right? So now you see, because the set is convex, right? This red part, this red circle will be always longer than the black circle. Okay. So for each r, this will be positive. For each r, this will be non-negative. I mean, not positive because it could be flat, right? It could be, well, actually in the limit for a bounded set, it will be, for a bounded convex set, it will be strictly positive if you do the integral over all r, over the all r. Huh? Well, actually here I have, if you remember Enrico Valdinocci's talk, when he was talking about the boundary stickiness for non-local minimizers of the non-local perimeter, this was a very similar argument with which we argued like this to exclude the what did he call it, the suspects, yes, the suspects in his example. So here, I should have started perhaps with the simpler example. Well, the half space, well, if you have a half space, you can do the same argument, right? And on the boundary, the two circles will always have the same length, right? The red one and the black one, so you get that the fractional mean curvature is 0. Well, so now let me come back to the Michael-Simon Sobolev inequality. The analogues of the Michael-Simon Sobolev inequality. So I want to have I recall here, right? So we had the Sobolev inequality on a manifold where this is just the Sobolev where we added, okay, to get the universal constant, we added a term involving the mean curvature. Okay. So first just let me recall the fractional Sobolev inequality in the flat case, not on a manifold. So you have the critical fractional Sobolev exponents np over n minus sp, and then you have this well-known Sobolev fractional Sobolev inequality. LP star is smaller than the Gallardo seminorm of U. Well, let me just give an example here to make a connection, another connection with the fractional perimeter. If you plug in here, if you take p equal to 1 and you the characteristic function of a set E, right here on the left side, you just get the measure of E to some power. And on the right side, okay, U is either 1 or 0, right? It is 1. U of x is 1 is if x is in the set E, and U of y is 1 if y is in the set E. So this will be always 0 if x and y are both in the set E, and it will be also always 0 if neither of them are in the set E. So one has to be in the set and the other not, or vice versa, right? So that's why you get here integral of E complement, right? E complement. So then you get here the twice, well, up to a constant. That's why I forget about the constant. Twice the fractional perimeter of the set E. I could have, this would have been another good motivation to introduce the fractional perimeter, because it's completely analogous to the local case, where you also, if you take the L1 norm of the gradient and you plug in the characteristic function, you get the perimeter of the set. So now what do we do on the manifold? So on a manifold, we define the Gallardo seminorm exactly the same way, right? But you just do the integrals over M. Huh? So Mi here for me is an n-dimensional manifold. Huh? Embedded there are n plus 1, so codimension 1 manifold. And here below, it is this modulus x minus y is the distance in the ambient space. Okay, that's the only difference. So the question is, how would a fractional Sobolev inequality on a manifold look like? And the first generalization has been obtained by Cabre and Cozzi. Okay, okay, so let's assume that only for a special class of manifolds which are like a minimal surface or alpha minimal surface, and then it looks exactly as the fractional Sobolev inequality in the flat case. There's no additional term, right? You can estimate everything by the Gallardo semi-norm. More precisely, okay, they had these two applications in mind, especially alpha minimal surfaces, but the only thing you really need is a density estimate of this sort. Okay, let me draw better a picture for the density estimate. So what you need as the manifold somehow always grows, okay? It goes, I mean, it has to go here out of the screen and then out of the room and so on. And so on. So what you need is that if you intersect the manifold with balls, right, then this measure, the intersection, this black one, has to grow as R grows, okay, to the appropriate power, which is depends on the dimension. Okay. And obviously this cannot hold for a compact manifold. I mean, you can plug in, if your M were compact, right, just take U equal to 1. Plug in the function U equal to 1 into this inequality. Here you get 0 because it's 1 minus 1. The integrand is 0. And here you get the measure of the manifold. So of course, a compact manifold cannot, this is what I said, a compact manifold cannot satisfy the density estimate, right? If you take big balls enough, right, then you will, for all balls big enough, your measure so manifold intersected with the ball will have the same measure as the manifold, right? So you cannot have this density estimate. So the question is, what do we have in this? What can we get in this case? So what is the term that should come here? And this is exactly the type of result that we obtained. So we want here a universal constant independent of the manifold. So the result of this type is here for convex. We have, let's say, omega is convex and the manifold is the boundary of that convex set. Compact or not, that is not required. Then you get something analogous to the Michael-Simon, the classical Michael-Simon Sobolev inequality, where you add to the Gallardo semi-norm the LP norm of U on the manifold, and you have to weight it by the fractional mean curvature to the power P. And then you can have here a constant independent of the manifold. So let me give you an example. So again, I take the whole M to be the whole manifold. I mean the boundary of my convex set. I take U equal to 1. Okay, if U equal to 1, again, the Gallardo semi-norm disappears, and I only have this term. Right? I only have this term, and here I get this estimate for the measure of the perimeter of omega. I can estimate it in terms of an integral of the non-local mean curvature. Okay, actually, I will comment on this immediately. This is very special for convex set. You have something even stronger. You have a pointwise inequality. Right? If pointwise, I mean because this inequality here, I estimate some power of the perimeter by a universal constant times the fractional mean curvature at the point x for all x, for any point on the boundary. If you integrate this, you see, if you take this to the power p, this inequality, you take it to the power p and integrate over the boundary, you take exactly this. You obtain the integrated version. So this is very special. This is something that can only happen in a non-local setting, right? It has no, because in a local setting, even if you have a convex set, this could be 0, right? Let's say if it has flat parts, then the curvature will be 0, and this can be something positive. So you see how that the non-local mean curvature somehow takes into account globally the behavior of the set and not only the curvature near a point. That's why you have a chance of getting such an estimate. And the other thing about special is this can only hold for convex sets, even for in the non-local setting, because you can easily construct a set with some measure, finite measures, so that the fractional mean curvature and at some point of the boundary is zero or arbitrarily small. Okay, so this last estimate, this is what we use to get an extinction time for the fractional mean curvature flow. Okay, so here we have if omega 0 is convex, if the initial set is convex, then okay, this part is very similar to the argument of Evans and Sprook. So once you get the Michael-Simon Sobolev inequality with the universal constant, you also get an extinction time. So an extinction time is smaller than some constant times. Here I have the perimeter of the initial set to some power. Of course, I didn't introduce the non-local fractional or the fractional mean curvature flow, which is exactly the same as I did. The concept is exactly the same as I did for the classical mean curvature flow, except that you replace the mean curvature by the non-local mean curvature in that PDE defining the flow. Okay, so here is analogous to the local case. Previously, with monotonicity argument, you can obtain that the extinction time can always be estimated by the diameter to some power. So the improvement is that it's not the diameter, but the perimeter of the set. Well, now I have so I have 2 more slides, so I think I'll just be right in the time. I will have some selected ideas of the proof. Okay, well, first I will give you a very simple argument, which was actually somehow the initial idea, which somehow the breakthrough idea, which led to this inequality. So I will show you this pointwise inequality that I talked about. Well, of course, for a curve n equal to 1, which means a set in R2, and in this special case. So how can you show this? So here I want to show this estimate for all x on the domain. So I can assume, I can turn the domain a bit, and I can assume that x is 0. And I can also turn also assume that the tangent plane touching the convex set is this horizontal thing. So now I take perhaps a bit strange parametrization of the boundary. I take a parametrization where I have an angle t, which goes from 0 all over to pi, and to each t I have a unique distance. This point on the boundary to the other point of the boundary, which I take RT. So this is the parametrization that I take. Okay, so, well, I take this to calculate the perimeter, and I take this R of t. Well, this is not a parametrization, because here I have a solid integral. So I calculate the non-local mean curvature at 0. Okay, here you would have y minus 0, right? But y minus 0 is y. So that's why I have this term here. And what do I observe first? First, observe that, okay, here you have the complement, the characteristic function of the complement, right? So when you integrate over the complement, you have ones here. All this will be complement, right? But there will be an integral. The integral is over whole R2, but there will be integral also over the domain, right? So when these points in the complement, you integrate over this, will cancel with when you integrate over these points in the domain, right? We'll give exactly the same value, right? that will cancel. So by that cancellation, in the end, what do you get? You only get the integral over points in the complement, but not all of them. You omit the terms which would be in this symmetry, this part of the domain, right? I call this R plus and R minus, and now you get because of the symmetry, you get that this is 2 times just R plus, right? And now this integral you calculate with radial integration. Yes, for each t, you integrate from 0. Well, not from 0 because you only integrate over R plus, from R of t to infinity. Okay, so you integrate from R of t to infinity, and this one-dimensional integral you can calculate explicitly. It's only just a power function, right? And you get this thing. Okay, the second integral you leave as it is. It's from 0 to pi. That you cannot calculate. It depends, of course, on the domain. So this is the fractional in curvature at the point 0. And the boundary, the length of the boundary, right? I mean, using this parametrization, you derive the parametrization, you get R square and R dot square, right? And I have here to the power minus S, right? Because I have this to the power minus S, if I omit something, I will omit this R dot, I will get something bigger, right? So I calculated the left side and the right side. And I have to show that the left side is smaller than the right side. And you see this is nothing else, just Jensen inequality, Jensen or Hölder, right? Because this is convex. The to the power minus S is a convex function. So I have proven this one. Well, you see the power, the constant will be something like, you have to divide by the length pi 2 over pi times S or something like that. And it is universal, as you see. It doesn't depend neither on the point nor on the domain. Okay. Well, from this, there's still a long way to get the general inequality. So I give you just some comments on the ingredients. So what I did, the previous argument, okay, let me recall the condition in the Cabre-Cozzi result, right? You had something like a density estimate, right? So here I have shown that this is precisely what you don't have a density estimate in the setting of the previous case, right? But what you have to show to get the general result, well, not just, I have to show this also for subsets of the boundary. If I take E, the subset of the boundary, right, I want to have some kind of density estimate. So this leads to the dichotomy idea. If you have small density, then you're precisely in the case of the previous setting, right? Then you can carry out somehow the argument that I did before. Well, I mean, in terms of the set E, I mean, you can imagine if the set E, if the set E becomes very, very small, right? The density, okay, is not exactly will be this. If the set E is very, very small, this is a negative power, this will go to infinity. You cannot have something like this. But if the set E is very small, let's say an arbitrarily short interval, this is a singular integral, huh? This will be very singular, and not only this side blows up, but this side also blows up. So then this thing will save you, okay? Well, it's not that simple, but essentially you distinguish two cases, okay? And for each subset of the domain, you get either this estimate or this estimate. The proof of this estimate is not like in the Cabre-Cozzi result. Huh? It's very different, but let's say the idea comes from there. Okay? So this dichotomy argument, okay, is quite involved. So it uses a rearrangement argument. Thereby, I mean that you essentially can symmetrize. You can only consider sets E, which are intersections of balls with the boundary of the domain. You use a double layer potential identity. You use a reverse perimeter energy estimate for convex sets. Reverse I mean in comparison to minimizing minimal surfaces. So for convex sets, you have something reverse. Well, there's some powers involved. You use an isodiametric inequality for perimeter of convex sets. Here I mean that isodiametric inequality estimates the measure of a set by its diameter. And for convex sets, you can estimate the perimeter of the convex set by its diameter. And you use the relative isoperimetric inequality in box. Okay, so a lot of tools enter this, but in the end, if you can show this dichotomy, then you just sum up the two, right? Because one of the two cases occurs, right? If one of the two cases occurs, then you sum up the two. Okay, so this is smaller than this plus HS. And then if you integrate this, okay, I just want to get an isoperimetric inequality in the end. If you integrate this, these two terms, right? Here you get exactly, you see like the Gallardo semi-norm, right? Well, half of it, because you don't have a double integral. But if you integrate over the set E, you get here the perimeter, the fractional perimeter on the boundary, and here you get the integral over the mean curvature. Okay, so you get, okay, I didn't show you the Sobolev, but I have proven, well, I didn't prove, I just gave you ideas. You get isoperimetric, a fractional isoperimetric inequality on your manifold. So I cannot talk more about the proof because it's quite involved, but I thank you for the organizers who allow these nice long-range interactions between India and my place. It keeps me active, and I thank them a lot for the effort. Okay.
Okay.
I give it back to you, Prosenjit, right?
Yeah. Okay.
I continue sharing the screen?
Yeah. I mean, if there is a question, maybe it is required.
It is required. Okay. Okay.
So thank you, Gyula, for the wonderful talk. And now I request all the participants to put their question and answer in question and answer box, or they can raise their hand. We can unmute their mic. Okay. So please feel free to ask your questions and queries to Professor Chato.
Hello, Professor Chato.
Yes, I can hear you.
Okay, so my question is regarding the Cabret-Cauchy inequality. So that result says that if the mean curvature is zero.
Let me go to that result. It's quick, right? Cabret-Cauchy. Okay, here, this one, right?
Yeah, no, 2019.
Ah, that's a Cabret-Cauchy Chato. Sorry. This one.
Yes. This is a one directional statement. That is, if the curvature is zero, then this inequality holds. Do we have any characterization of surfaces for which this inequality holds?
Okay, first of all, if it is in one direction, that's right. So, but it's not if the curvature is zero. It says that's just the first statement. The more precise statement, if there is a density estimate, right, then such an inequality holds. So it's stronger than just we don't need, the curvature could be positive, negative, or change. Important is the density estimate. So actually, minimal surfaces and alpha minimal surfaces, they both satisfy this density estimate. Okay, so your question is, if such an inequality holds, do we have to have a density estimate?
Yes.
That is your question.
More precisely, more generally, we can talk about characterization of surfaces for which this inequality holds.
I expect I don't know, but I expect that something like, I mean, the counterexamples show that such a density, if a density estimate doesn't hold, then such an inequality cannot hold. I don't know, but I expect that that there should be perhaps a characterization that you're looking for.
Okay.
Okay.
And what about the sharpness of the constants?
Oh, that is very difficult. Okay. That is very difficult. So even in the classical Michael-Simon Sobolev, the local case, the sharpness of the constant was open until now for 40 years. It was proven last year by, what was his name? It's coming, sorry. Okay, it was only proven last year in the classical case.
Okay.
Okay, so our results are far from giving the best constant. Okay, you can easily see that. Okay, if you go from this pointwise one, okay, if you have first a pointwise one and then you do the integral, you cannot get the best constant. This constant has to let me just think. Okay, here I get the constant universal depending on S and N. The argument, if I get S go to 1, yeah, of course, here has to be, there's no, the proof I gave you, you remember, there's no factor 1 minus S appearing. There you already see. Okay, here if you do this argument, there's no factor 1 minus S appearing. Here I get the best constant and it will be something like this to some power perhaps. It has to, if you want to have the best constant, a 1 minus S has to appear, because when you let S go to 1,
the BBM formula type.
Yeah, this HS, no, not the HS, but the fractional perimeter will blow up, right? So you have to compensate that somehow. You see what I mean? That would be one argument showing that, let me go back to, you wanted to the Cabret-Cozzi result here. Okay. Yeah, that's perhaps an argument where you can show that you cannot get the best constant.
Yes. Thank you.
You're welcome.
Okay. So are there any more questions? So I have a question.
Yes?
Yeah. So once you have the
I cannot hear you right now. The sound has disappeared. Can you hear me? I cannot hear anything. Where can I? Now I can hear again.
Oh, okay, good.
Okay, so you, okay. Okay, now I can hear again.
Yeah. So once you have the isoperimetric inequality, do you then get immediately Sobolev as in Euclidean and local case by Q-area formula and Holder inequality?
Okay. You mean the very last slide?
Yeah.
Okay, so there are two questions here. The question is first, even in the classical case on a manifold, the classical Michael-Simon Sobolev, once you have their isoperimetric inequality on the manifold, yes, you immediately get, very simply, the Sobolev inequality, right? But now actually in the non-local case, if you have isoperimetric inequality, or in other words, Sobolev inequality for P equal to 1, then from there, it's not like in the local case. You cannot get the general Sobolev inequality for any P. Okay, that's still an open problem if there's some easy implication. So actually, the thing that I've written here is not very useful to get our final result. We actually use these pointwise inequalities, and we follow an argument by Savin and Baldinocci, a slicing argument to get the Sobolev inequality. That argument of Savin and Baldinocci applies. Okay, it's involved, but there's not. We can follow that very closely once we get the pointwise inequality. Okay, so the answer is no. In the non-local case, you do not get from isoperimetric p equal to 1 to general p. Okay, did that answer your question?
Yeah.
Okay.
Okay, are there any more questions? So in case there are no more questions, let us thank Professor Chato for this wonderful talk. And we meet again on next Thursday, this Thursday, at 3 p.m. for the talk of Professor Luca Esposito on local minimizers of free interface problem. Till then, goodbye, and I request all the participants to leave this platform. And thanks to Professor Chato again for this wonderful talk.
I thank also the organizers.
Bye-bye.
Bye-bye.